Welcome to the Cisco Netacad Introduction to Networks video series by Jason Johnson. This video is Module 4. Module 4, the physical layer. We're going to be looking at the physical layer in this module. We're going to be looking at the purpose of the physical layer, the layer characteristics. We're also going to be taking a look at copper cabling, UTP cabling or unshielded twisted pair cabling, and how that's used in Ethernet networks, fiber optic cabling, and wireless media. Now, we've talked about some of those before in previous modules, but now we're going to take a more in-depth look at them. Purpose of the physical layer. The physical connection needs to take place before any communications can occur. A physical connection to a local network must be established. You have to have that wired connection. The connection can be wired or wireless, and depending on the setup of the network. So it needs to be some type of wired or wireless, but you do have to have a connection. This generally applies whether you're considering a corporate office or a home office, small office, it doesn't matter. It needs to take place in all types of networks. A network interface card, or a NIC, connects a device to the network, and some devices may have just one NIC, while others may have multiple NICs, or wired or wireless, for example. An example of that would be some servers have multiple network cards in them for redundancy. Most servers that I've set up in the past have at least two, if not more, so that you can have multiple failure points. So if one card goes bad, you can pull it out and replace it, and the other ones will still work until you can get a chance to shut the server down and replace it. And not all physical connections offer the same level of performance. The physical layer transports bits across the network media. It accepts a complete frame from the data link layer and encodes it as a series of signals that are transmitted to the local media. This is the last step in the encapsulation process before it gets sent down the network, and the next device in the path to the destination receives the bits and re-encapsulates, I can't say that right, re-encapsulates, still can't say it right, the frame, then decides what to do with it. Capsulates. Yeah, there we go. Close enough. So it encapsulates it, sends it down, and re-encapsulates it or de-encapsulates it. Some say it different ways. Physical layer characteristics. Now we have here an OSI model, and we have our 7 layers: physical, data link, network, transport, session, presentation, and application. And if you remember the way I remember OSI, if you remember back to some of the previous modules, I said, please do not throw sausage pizza away, because I like pizza. I don't necessarily like sausage pizza, but I like pizza, and that's a good way for me to remember it. And the layer 1 is your physical layer. Layers 7 through 2, the TCP/IP standards are implemented in software and governed by the IETF. In the physical layer, they're implemented in hardware and are governed by a lot of different organizations: ISO, EIA, TIA, ANSI, IEEE. And if you remember back to some of the previous modules, I encouraged you to research some of those organizations. Hopefully you have by now, and research some of them and seen what they are responsible for. Now, in the physical components, physical layer standards address 3 functional areas: physical components, encoding, and signaling. The physical components are the hardware devices, the media, and other connectors that transmit the signals that represent the bits. Hardware components like NICs, interfaces, and connectors, cable materials, and cable designs are all specified in standards associated with the physical layer. Encoding converts the stream of bits into a format recognized by the next network device in the network path. The coding provides predictable patterns that can be recognized by the next device. And examples of encoding methods include Manchester, shown in the figure on to the right here. This is a digital signal that we're looking at here. And what would happen is they set a buffer. So this would be 0 down here, and this would be 1. But they set a baseline. So they say if the signal goes above a certain level, it's going to be a 1. And if it drops below a certain level, it's going to be a 0. And so you can turn that signal off and on like a light switch. It's on, they turn the signal off, it goes down, and then it comes back on, and that's your bits. So this range, and on the timing, if you remember back to previous modules, we talked about timing. So the timing of the network says, okay, by this amount of time, you should have received another signal. If you didn't, then it's off. So that's on, that's turned off, turns on, or turns turns off because the bulk of it was down, and then on, off. Let's take a look here at some other examples. The signaling method is how the bit values 1 and 0s are represented on the physical medium. The method of signaling will vary based on the type of medium being used. This is electrical signals over a copper cable. And you're going to see if you looked at the physical up and down, it kind of looks like a city skyline here, but it's not consistent. You don't see it like the previous model that we just looked at on the screen before. It's not just a straight up and down. Those signal strengths are going to vary depending upon the length, depending upon interference. There's different things that are going to keep that full signal from going. It just needs to be above that threshold. If that signal drops below the threshold, then it stops getting those packets through, and that's where we have packet loss. So if we look up here, this is fiber optics up here. We have fiber optics. This is light pulses. So depending upon the brightness of the pulse would be an on, and then the light pulse drops off, it goes off. And then a wavelength, this would be more like a radio wavelength. They're wireless. The wavelength goes up and down, kind of like tuning a radio, and it goes up and down, AM, FM radio, and it goes up and down. And then if it goes above a certain level, it's on. If it goes below a certain level, it goes off. Now, bandwidth is the capacity at which a medium can carry data. Digital bandwidth measures the amount of data that can flow from one place to another in a given amount of time, and how many bits can be transmitted in a second. So physical media properties, current technologies, and the laws of physics play a role in determining available bandwidth. Now, bandwidth is, you'll see BPS, KPS, it's by second. So it's kilobytes a second, bits per second. It's not the same as when you're measuring speeds on a central processing unit. This is bits per second. How many bits are going through in a second? I kind of think of the bandwidth. I use the analogy of a highway or a road. Is it a 1-lane highway, or is it a 4-lane highway, or is it an 8-lane highway? If it's a 1-lane dirt road, you're probably going to be able to get maybe 1 bit per second down that 1-lane road. But if it's an 8-lane highway, you might be able to be putting terabits per second down that 8-lane highway. They're sending all those cars down at the same time because you have multiple paths, or you have bandwidth. Now, some of the bandwidth terminology that you will see, and you need to know these terms. One is latency. That's the amount of time, including delays, for data to travel from one point to another. So that's latency. How long is it going to take to get there? Throughput is the measure of the transfer of bits across the media over a given period of time. And goodput is the measure of usable data transferred over a period of time. So goodput equals throughput minus your traffic overhead. So I look at throughput and goodput, mainly throughput. If you're going to, I use the analogy of that's how many cars are on the highway. So if we have that 4-lane freeway, that's our bandwidth. And then our throughput is how many cars are on that highway at a time. If we've got full rush hour traffic on that highway, we're going to get latency because it's going to take longer for our bits to get there. And so that's what our goodput would be if it equals our throughput minus our traffic overhead, how much traffic is going across the network. Copper cabling. The characteristics of copper cabling, it's the most common type of cabling used in networks today. It's inexpensive, it's easy to install, and it has low resistance to electrical current flow. Now, some of the terms you need to understand and know about copper is attenuation, and not just copper, it's all networks, but attenuation, that's the longer the electrical signal travels, the weaker they get. So you only have so far. So if you're sending, it's almost like talking to someone. If I'm standing a foot away from you, you're going to be able to hear me really well. If you're standing 100 feet away from me, you're not going to be able to hear me as well. So I'm going to have to talk louder, or we're going to have somebody repeat it in between. A switch would be handy to do that. Somebody standing in the middle relaying that message for us. But that's attenuation. The longer the signal travels, the weaker it gets. The electrical signal is susceptible to interference from 2 different sources, which can distort and corrupt data signals: electromagnetic interference, or EMI, and radio frequency interference, RFI, and crosstalk. So if you put electrical lines or copper cabling up next to one that I can think of is the lighting. If you have fluorescent lighting, it's going to have interference on it, and you're going to lose. You're going to get interference, and you're going to lose signal. So now mitigation is another term. That's strict adherence to cable length limits will mitigate attenuation. So if you want to mitigate your signal loss and your attenuation, you want to only put your cables out to the recommended length for that particular type of cable. Cat 5, Cat 6, they all have different recommended lengths. Some types of copper cable can mitigate EMI and RFI by using metallic shielding and grounding. And then some types of copper cable mitigate crosstalk by twisting opposing circuit pair wires together. And we're going to talk about those here in just a minute. Some of the types of copper cabling that you have will unshielded twisted pair, or you'll see UTP. Unshielded twisted pair means there's no shielding on it, which means you're going to get more interference. If you put it up next to a fluorescent light or you put it close to electrical lines or something like that, you're going to get more interference. Shielded twisted pair, or STP, has this metal shielding around it, wrapped around it. So you have your twisted pair, your wires are twisted to help with the attenuation, makes it travel further. And you have this metal around here, and that helps it shield from any EMI or any other type of interference. This cabling is more expensive because it does cost more money to put that metal around the shielding and the twist. And another note I will say here, some cabling is cheaper than others, and this is just note outside of the classroom. This is my personal experience. Some cabling will be more expensive and some cabling will be less expensive. You want to make sure that you're checking the twist per length or twist per yard or twist per feet. Some companies calculate it differently. Depending on how much twist you have in this, you're going to have more attenuation or you're going to have more length. Some cheaper cabling will not put as much twist in their wires. And so it's cheaper to do that because you use less wire, you use less you lose less resources to create that, but it is cheaper because it doesn't hold as well. So you want to, when you're putting in wiring, you want to make sure that you get good wiring, that has good twist to it, and if you're getting shielded twisted pair, that it has good shielding to it. And then here's this coax cable down here. If you've ever worked with cabling, video cabling, you've seen coax cable. If you've ever put in a cable TV into your house or looked at that cable, that's coax RG6. It goes by RG6 in a lot of cases. There's some other forms of it, but the most common type is RG6. Has a common inner line here. You have this plastic sheathing, and then you have some copper metal around here, and then you have this cross. Basically, it's a mesh that cuts down on any interference, and then you have this other plastic sheathing out here. Now, unshielded twisted pair, it's the most common networking media. It's the most inexpensive because it doesn't have shielding, and you have just the plastic sheathing, and then you have the wires. It's terminated with an RJ45 connector, and it interconnects host with intermediary network devices. The key characteristic is the outer jacket protects the copper wires from physical damage, and twisted pairs protect the signal from interference, and color-coded plastic insulation, this color coding here, insulates each wire insulates the wires from each other. So you have this plastic coating here, which insulates it from damage, and then each of these are fun. You have orange, white, and most of all of your unshielded twisted pair and shielded twisted pair that you use for your copper cabling is all going to have the same color pattern. You're going to have orange, green, blue, and brown. Orange, green, blue, and brown. Now, it'll be different shades of it. Sometimes I've seen stuff that almost looks red, and I've seen some that almost look blue, like two different shades of blue, and then this brown almost looked white. But you'll have a orange white, green white, blue white, and a brown white. And now the white version of it will have a blue stripe on it, or a brown stripe with white, so it'll be interlaced. And if you pull a wire apart, if you have access to pull some of these wires apart, it's good to get your hands on that. In the labs, that if you're doing this Netacad course, in the lab, your instructor will show you some of this wire. And if you're in my lab, I'll show you some of this wire as well, and we'll do some cabling with that. The shielded twisted pair has the shielding around it, and it cuts down on the interference. It has better noise protection than UTP. It is more expensive because it takes more resources to make it. It is harder to install than UTP because it is a little bit stiffer, and so it's harder to move around corners. It's also terminated with RJ45 connectors. It also interconnects host with intermediary network devices. The key characteristics on this are the outer jacket protects the copper wires, the braided or foil shield provides EMI RFI protection, and the foil shield for each pair of wires provides EMFI. So you have shielding here, and then you have shielding here, and then you also have the same color coding. Blue, white, orange, white, green, white, brown, white. Now for coax cable, it consists of the following. You have an outer cable jacket to prevent minor physical damage, a woven copper braid, and then you have a layer of plastic, a flexible plastic insulation, and then you have your copper conductor. There's 3 different types of connectors. You do need to know these types of connectors. You have the B and C, the N-type, and the F-type. The properties of UTP cabling. UTP has 4 pairs of color-coded copper wires twisted together. There's no shielding, and UTP relies on the following properties to limit crosswalk. Cancellation, each wire in a pair of wires uses opposite polarity. So one wire is negative, the other wire is positive. They're twisted together, and the magnetic fields effectively cancel each other and outside EMI RFI. So by twisting them, they cancel out. They use the magnetic properties to cancel out interference. And the variations in twist per foot in each wire. Each wire is twisted at a different amount, so which helps prevent crosstalk amongst the wire and the cable. So this one might be twisted just a little bit less than this one right here. Now, UTP cabling standards and connectors, there are governing bodies for standards. The standards for UTP are established by the TIA-EIA, and that's the 568 standards. So it standardizes cable types, cable lengths, connectors, termination, and testing methods. The electrical standards for copper cabling are established by the IEEE, and that rates which cable according to its performance, whether it's a Cat 3, Cat 5, Cat 5e, Cat 6, or beyond. An older Cat 3, which you probably, if you're pulling out cable of a really old, and I would probably say 20 years old or more, you might find some Cat 3 cabling. It's not twisted. Cat 5 and 5e is more of the common of what you'll see today. It's a little bit less expensive than Cat 6, but most of what you're going to see today is Cat 6, is some form of Cat 6. An RJ45 connector looks just like this. You would slide the wires in. This is over here on the right-hand side. You slide the wires in. What you have to do is you have to cut the sheathing off, and then each one of these wires you have to stretch them out where they're all even, where they're not twisted anymore. You slide them up in here, and then you take a crimping tool, and then it pushes all these little gold teeth down onto the cable. A poorly terminated UTP cable looks like this. It's just all a big mess in there. You want them all nice and neat. So that's an RJ45 connector. An RJ45 socket is you don't have to push them up into this plastic sheathing or this plastic connector. You lay the wires across, like right here, and then there's a punch down tool that you use. And that punch down tool just punches those wires down into that holder. Now what we have here is a straight through and a crossover UTP cables. A Ethernet straight through both ends of the 568A or the 568B. Doesn't matter which one, either standard. Both ends are either A or B. That's a straight through. Now here, this is T568A and this is T568B. If you're doing a straight through, you just use either form. You either use it this way, and this is where we're looking at the green, white, green, orange, white, blue, blue, white, orange, brown, white, brown, and then 5.6b is orange. You see the orange here, and now they're using the green to do the cross to make the pair 3. Where over here we use pair 3 for our first two. An Ethernet crossover, one end is 568A and the other end is 568B. You use those for host to host, switch to switch, or router to router. A straight through, you would use a host to network device. And a rollover, which is really legacy now because most devices that we're using use auto MDIX or auto MDIX, and we'll talk about that here in a future slide. That's a rollover. That's just where you have one side and then you roll all of the cables over, but they're very rarely used anymore. It's a Cisco proprietary. But it was to host a serial port to a router or switch console port using an adapter. And most that you're going to see today are either a straight through or a crossover. And you don't really need crossovers much anymore either because the MDIX takes care of that. Now with fiber optic cabling, It's not as common as UTP because of the expense. It is a lot more expensive than copper cabling. It is ideal for some networking scenarios, though, when you want to have high speed and you want to have connections between servers, server rooms. If you're connecting between buildings, is when you usually are going to use fiber optics. It's less susceptible to attenuation, which means it can travel further. It's completely immune to EMI and RFI. So if you're going to have a place where you have a lot of electromagnetic interference, you're going to want to use some type of fiber optics. It's made of flexible, extremely thin strands of very pure glass. It uses a laser or LED to encode bits as pulses of light, and the fiber optic cables act as waveguide to transmit the light between the two ends with a minimal signal loss. And let's look here. So this is a single mode fiber. You have your glass core, you have your glass cladding, and then polymeric coating, plastic coating. And this is a single mode fiber. It just shoots the light down through the cable. Very small core, uses expensive lasers, and it's for long distance applications. The multi-mode fiber, I'm not saying that right. Multi-mode fiber has the same structure, but the light waves bounce through the cable because we're sending multiple paths of light through there. And it goes beyond this class on how that works, but you can go do some research if you're interested in how that actually works. You bounce multiple beams of light through the glass, and it allows for multiple paths. It has a larger core. It uses less expensive LEDs. LEDs transmit at different angles, and it's up to 10 gigabytes per second over 550 meters. So much longer distances than copper. The dispersion refers to the spreading out of light pulses over time. So instead of attenuation, we get what we call dispersion. Increased dispersion means increased signal loss of signal strength. MMF has a greater dispersion than SMF with a maximum cable distance of 550 meters. And if you cut a fiber optic line, it takes special tools to connect them back together. It takes special equipment. It takes special training. And it goes beyond the scope of this course. But typically it's going to take you a little bit of time to have bring a specialty person out, and then with their tools, and then it takes a lot of time to get a fiber optics cable connected back together. Whereas a copper cable, you can just put connectors in and be right back up and running. Now, fiber optic cabling, we use that in enterprise networks. It's used for backbone cabling, and that's between server rooms or between server racks. Fiber to home is used to provide always-on broadband services to home and small businesses. There are some places that have fiber now. I know Google was running fiber at one point. Long-haul networks used by service providers to connect countries and cities together. I know at my college, we have fiber optic lines running from our college to the next nearest town, which is about 60 miles away, but there are waypoints along the way that it gets picked up and retransmitted, but we're using fiber optics between the cities. And then you have submarine cable networks. Those are used to provide reliable, high-speed, high-capacity solutions capable of surviving in harsh undersea environments at transoceanic distances. Those are cables that they lay on the ocean floor. Some of the fiber optic connectors that you'll see... Oh, went too far. Some of the fiber optic connectors that you will see are straight-tip ST connectors. You'll see subscriber connectors, Lucent connectors, or duplex multi-mode connectors. You'll typically, if you're going to use fiber optic cables, you'll buy them pre-made. These are patch cords. So if you're going to go between servers, so if you're going to go between routers that have fiber cards in those, you're going to use some type of pre-made cable at a particular length. It's pre-made. You're not gonna cut your own cable and make your own fiber optic cable. Unless you have special training and special tools, but you're going to use what they call the patch cords. And a yellow jacket is for single mode, and orange or aqua is for multi-mode fiber. Now, fiber versus copper, UTP cabling supports 10 megabytes a second up to 10 gigabytes a second. Fiber optic cable goes from 10 megabytes up to 100 gigabytes. So much greater speed, bandwidth. Distance, about 100 to 100 meters. This one goes from about 100 to 100,000 meters. Immunity MFI, it's low. It's high, it's completely immune. This one's fiber's completely immune to electrical hazards. The median connector costs are low. The installation skills are low, and the safety precautions are low for cabling, UTP cabling, but for fiber, it's all high. It's going to be expensive. The installation skills required, or they take a lot to learn how to do fiber, and the safety precautions. You have to be really careful because if you bend the fiber wire too much, it'll snap the glass. And if you have stuff cut through it, or it's much more delicate than copper. Now, wireless media, you have properties of the wireless media. It carries electromagnetic signals representing binary digits using radio or microwave frequencies. This provides the greatest mobility option. Wireless connections numbers continue to increase. You've got towers going up all over the place, and then now you've got cell phone towers that are going up. That's also considered wireless media. The coverage area. The effective coverage area can be significantly impacted by the physical characteristics of the deployment. So if it's on top of a hill, you're going to get better coverage than if it's down in a valley. Interference, it is susceptible to interference and can be disrupted by many different common devices. Wireless communication coverage requires no access to a physical strand of media, so anyone can gain access to the transmission. And shared medium wireless LANs operate in half duplex, which means only one device can send or receive at a time. Many users accessing a WLAN simultaneously results in reduced bandwidth for each user. Now, the IEEE and telecommunications industry standards for wireless data communications cover both data link and physical layers. And in each of these standards, physical layers specifications dictate data to radio signal encoding methods, frequency and power transmission, signal reception and decoding requirements, antenna design, and some of the standards are Wi-Fi, is governed by IEEE 802.11, Bluetooth is IEEE 802.15, WiMAX is 802.16, and Zigbee is 802.15.4. That's primarily for Internet of Things applications. In general, a wireless LAN requires the following devices. You have to have a wireless access point. Some call them a WAP or an AP. You'll hear the term AP or WAP. That's a wireless access point that concentrate wireless signals from users and connects to existing copper-based network infrastructure. So you'll connect to a wireless access point to a copper point. You've usually seen these in home networking. You'll buy a wireless router from your local Best Buy or Walmart or one of your local stores, and you'll plug it in, and then it transmits wireless. That's a wireless access point. Your wireless NIC adapters provide wireless communications capability to network hosts, and those are typically in your laptops, your mobile devices, your handheld devices. Now, there are a number of WLAN standards. When purchasing WLAN equipment, ensure compatibility and interoperability. There's different versions, so you want to make sure you get the right version. Okay, so this has been the Module 4. Some of the things that we've learned are that before any network communications can occur, a physical connection needs to be made. Physical layer consists of electronic circuitry, media, and connectors. The physical layer standards address 3 functional areas: physical, encoding, and signaling. You have 3 different types of copper cabling: UTP, SDP, and coax. UTP cabling conforms to the standards established by the TIA-EIA, and the characteristics of copper cabling are defined by the IEEE. Main cable types that are obtained by using specific wiring conventions are Ethernet, straight through, and Ethernet crossover. You have optic fiber cable transmits over long distances. There's 4 different types of fiber optic connectors. You do need to know these. You need to know the different types: ST, SC, LC, and LC multimode. And that the fiber optic patch cords include SC multimode, LC single mode, ST LC multimode, and SC ST single mode. And then we also looked at wireless media. They can carry signals over bits over radio, microwave frequencies. We have Bluetooth. You have all kinds of different frequencies that you can use. And wireless does have some limitations, such as coverage area, interference, and security. And then we also looked at the different standards. You do need to know these standards, by the way, for the certification. So you want to make sure that you learn these: 802.11 and which one they are. 802.15, 802.16. And then we also looked at wireless LAN. It requires a wireless access point and a wireless NIC adapter. Okay, this has been Module 4. I hope it was helpful. Make sure you click the subscribe button below, and I hope you have a great day.